someday everyone's going to go, let's get science-y right after I say that, to be honest.
Let's put it on the back of the card like that.
Good. I think it says something about science-y on it.
Let's invent it.
Anyway.
Wear t-shirts.
Okay, so tonight we have Brenda Hunda. She's here.
Thank you.
She's here from the Cincinnati Museum Center, which has the largest collection of upper ordovician
Yes, well done.
fossils in the world.
Yes.
Very cool, very cool. So Brenda Hunda got her Bachelor of Science with honors in paleontology from the University of Alberta, Master's in Earth Science from the University of Alberta, and then a PhD in Earth Sciences at the University of California. And we're going to learn about geological foundations of modern landscape evolution. Take it away.
Thank you. So, thanks for having me. Thanks for coming out tonight. It was pretty gross out there. A lot of traffic, accidents, and things. So I really appreciate it. CJ said that I'm from the Museum Center. I've been there for 18 years now, which is hard to believe. I'm the curator of invertebrate paleontology there, so my specialty is fossils, particularly in this area. I did my PhD in this region. I do fossil stuff all the time. Just as a plug, we are opening a new geology gallery in the fall of 2023, which is going to be called Ancient Worlds, and it is going to highlight the geology of the tri-state region. So it's really exciting, and that's what my life is going to be for the next 10 months, essentially. But aside from that, I am not I have training in lots of geology areas. Landslides and natural disasters are my hobby. I love them. I love natural disasters of all kinds. I know that's a very weird sentence to say. I don't love people getting hurt. I don't love property being damaged. I don't love all of that. What I do love is that the earth reminds us every once in a while that it's in control and that it's dynamic and incredibly powerful. And, I think we all live our lives, driving from Kroger to home, to school, to work, to Kroger, to home, to school, to work, to Kroger, to home, to school, to work. Every day we have our blinders on. We don't really see the landscape around us. We don't really think about how the earth is operating. Why would we? I do every day, but we don't typically do that until something like this happens, or unfortunately tornadoes and hurricanes and things that remind us that the earth is constantly changing and that we just happen to be in the way sometimes, right? And that the processes that we see don't just happen on the East Coast or the West Coast. They don't just happen in Florida, and they don't just happen 10,000 years ago. They happen here, and they happen today, and they happen all the time. So once we get through this talk, you may feel slightly depressed. I don't want you to be depressed. It's the holiday season. I have some good things at the end to share with you about some positive aspects of landslide geology. But the landslide story, which you see on the news every once in a while with Columbia Parkway failing, this is on Elberon Avenue in 2014 when we had a major spring rain. I was very lucky to accidentally be driving up Elberon when this was failing and get out and watch it. It was one of these kismet moments where I just I'm just going to watch the whole thing come down, because that's a work of art right there. And once you start seeing the signs of landslides and the ways that we mitigate landslides in Cincinnati and the architecture that we have to do that, you'll start seeing it everywhere over Cincinnati. Our hills are held up by infrastructure designed to mitigate, I'm not going to say prevent necessarily, but mitigate landslides. And so once you start seeing what that looks like, you're going to see it absolutely everywhere. So let's get started. So, I have this fancy thing I forgot. Me and a rock hammer, fantastic relationship. Me and technology, not so great. And so I want to start out by saying that the geologic history of landslides in our area goes back about 500 million years, 450 million years. And if any of you have been stuck at the cut in the hill, in a traffic accident or just traffic, and look at that nice, beautiful cut on the side, those rocks are 450 million years old. And so this is a geologic time scale. Our Earth is 4.567 billion years old. On the left-hand column, because I don't have a pointer, is from 0 to 4.6 billion. And then that little tiny non-red portion at the top is expanded in the center. That's the last 600 million years of geologic time. The reason why it's expanded out like that is because, generally speaking, although we are learning a lot more these days, the origin of complex metazoan life, that's multicellularity, begins at about 600 million. So for most of Earth's history, things have been unicellular. They've been like algae and bacteria and fun things like that, and protists. In the last 600 to 700 million, like I said, we're pushing that date further and further back every time we make new discoveries. We are seeing basically the advent of complex metazoan life. For someone like me who studies trilobites, really, that's where things begin to get interesting. Is at about 600 million years ago. And that red bar right there is in the late Ordovician period, which is what the rocks are that you are seeing all around the cut in the hill, the 275 interstate. And if you could completely denude the landscape of everything, structures, vegetation, all the hillsides that you see from the bottom to the top are made of that. Okay? That is, except for some glacial sediments at the top, which we'll talk about, we really are dealing with mostly Ordovician bedrock. And we're going to explain why that's important for our landslides and how it got here. The next thing we're going to do is we're going to skip basically 448 million years, right? Most of that is actually not present here in the Cincinnati area. Some of it is present in Ohio, like in eastern Ohio and other parts of the state, in Kentucky and Indiana. But for our purposes, we're going to focus really on the last 2 to 5 million years in the Quaternary, and focusing on sort of like the Pleistocene, which is, Ice Age megafauna time, right? Mastodons, mammoths, all those good things. Because that is a series of events that have happened to help shape our landscape, which then leads to landslides. So we're really going to focus on those two areas. But in order for us to really think about what was happening on Earth 450 million years ago, we have to go back in time. So one of the reasons why I love paleontology and geology is because it's the only thing we have for time travel, really. That's like the real deal, right? We can go back in time to 450 million years ago and look at what the Earth looked like back then. So is everybody pretty familiar with plate tectonics, right? So we know that over time, continental positions shift. We know that ocean basin configurations change. This happens at about the rate that you grow a fingernail. Over the course of hundreds of millions of years, continents have traversed the globe and so forth. So we can imagine, by the way, I love plate tectonics. You got any questions about plate tectonics? I'm your gal. It's one of my favorite subjects outside of fossils. But if we look back at what the Earth looked like 450 million years ago, there's a few things I want to point out. First is that most of the land is in the southern hemisphere. Right? So we're not seeing Europe or anything like that in the northern hemisphere. We're not seeing North America predominantly in the northern hemisphere. We got little bits of it here and there. The red star is where we are located, here. And the white outlines are really just to kind of give you a general view of what continent we're on, but those places did not exist. Okay? So everything that you see that's green is all that was above sea level. Everything else was inundated by the sea. So we had a very high sea level today. And what that meant was that the sea level, the water just actually inundated our continents, what we call epicontinental or riparian seas. We don't have really a modern analog to this today because sea level is much lower than it was back in the late Ordovician. But most of the North American continent that was built at that time was flooded with water, such that if you were in Cincinnati, you would be under about 150 feet of ocean water right now. Yes, yes. There were no glaciers on Earth during this time, unlike today where we do have glaciers. So we had much higher sea level. Glaciers do come in a little bit later and drop sea level significantly, but for our purposes at this point, they do not. So a couple things to point out. The star is in the southern hemisphere, okay? So where we are located today as a continent is the furthest north we've ever been in North American history, okay? In fact, most of North America's history, North America I'm going to put in quotes, and I'll tell you why in a minute, North America's history is mostly the southern hemisphere continent. Most of our billions of years of being on this planet as what we recognize as the core of North America was actually in the southern hemisphere. The other thing I mentioned is that the blue is the ocean and the green is the land. that's exposed. The blue, we are inundated by a shallow marine tropical ocean. This is a place where you would want to go snorkeling or scuba diving or go for a cruise on vacation. Okay? So, very warm, very tropical, very shallow, light penetrating all the way to the bottom. In that ocean was amazing amounts of life. We're not going to have much time to talk about that today. We can do that next time. But amazing diversity of animals and algae and all kinds of communities of fossil, mostly invertebrates. Fish weren't here yet, even though they had evolved on Earth by this time. But we're talking about no amphibians yet have made the scene. There's no mammals, there's no reptiles, there's no birds, there's no people, despite what the Creationist Museum says. So, I have the fossil record to prove it, okay? And so, a couple of other interesting points. Life on land, the pieces that you see that are exposed are barren. We do have fossil records of plant spores going back to 475 million years that are from organisms like bryophytes and liverworts. So the non-vascular plants that may very well have skirted lagoons and shorelines and things like that. But as far as having anything that is fully terrestrialized with xylem and phloem and all the good vascular things that you would need to be terrestrial, that does not exist yet. Okay, so the lands are going to be mostly barren. There is no life that we know of from the animal world on land yet either. Always subject to change with new discoveries, but at this point, there's no evidence to suggest that at all. A couple of other wonderful things. The continent piece that's labeled Siberia up there to the upper right of us. Of course, that's the Siberian subcontinent. That's going to be our closest neighbor, which I always think about like politics today and how politics would be over there back then with Siberia as our closest neighbor. Baltica is in the middle there. That's the Baltic states like Norway, Sweden, Finland, Denmark, and parts of Northern Europe. Interestingly, Baltica is going to come and collide with us a little bit later in time to create the Caledonian mountain range and to create a megacontinent called Laurussia. So at one point, Northern Europe and those countries were part of us, and then they split off later again. Very dynamic. What you can see beneath Baltica, though, is that there's a section called Avalonia, and then to the left of that is a little tiny writing that says New England and Nova Scotia. So North America is not North America as we know it yet. Continents grow and change as plates come together and separate and come together and separate. And most of the eastern seaboard of the United States and Canada, the maritime provinces, New England, all that region, which, by the way, I'm Canadian and thought was like a state because you guys have a New England football team, and that is just rude, okay? For somebody who's challenged at geography, I'm like, where's New England on the map? And they're like, Brenda. And I'm like, come on, you guys have a football team. Seriously. Anyway, New England, all of these guys are going to come up and eventually accrete to the eastern margin of the United States. There's also no Texas yet. There's no Florida. There's no California. There's no anything on the West Coast. Our continent is being built. It's like all other continents over the next 450 million years. And that's why we don't call it North America. Because even though the central craton, that is the basement rocks that form our continent, are present, the coasts and everything as we recognize them are not built yet. So geologists refer to proto-North America as Laurentia. Okay, that's what we're going to call it from now on, I think. Laurentia. And that is before we recognize it as North America. It only truly becomes North America when T-Rex is hanging out on it. Okay? So we recognize North America as North America and officially call it North America in the Cretaceous time period. But before that, it is not completely built. And that's because we're finishing up the building of the eastern seaboard, and by Cretaceous time, we're starting to build up the western seaboard. And the reason why you can see these building, what we call continental accretion, is because we have mountain ranges on each side of the continent, right? We have the Rockies on the west and the Appalachians on the east. Mountains are signs of collision, mainly. There are exceptions to those rules, but for our purposes, they are signs of collision. So we're going to have one of our first collisions. There are 3 major collisions on the eastern seaboard. So I want you to think about the fact that today, most of the tectonic activity and all the excitement happens on the west coast, right, with earthquakes and all things. And the East Coast is really quiet. 450 million years ago, all the excitement was happening on the East Coast, and the West Coast is really quiet. So the East Coast is called an active margin, and the West Coast is called a passive margin back then. And what we see at about 470 million years ago is the start of a volcanic island arc chain. A modern example of that would be like Japan or Indonesia, coming in and slamming into the eastern margin of North America. Basically, anywhere that you think the Appalachians are today, that's the foundation of the building of the Appalachian mountain range. So the Appalachians are actually 450 so odd million years old, which is why they're so round and beautiful as opposed to peaky and like the Rockies, which are only 50 million years old. Okay? This volcanic island arc chain, or Japan, if you will, is known as the tectonic arc. It has volcanoes on it. We have volcanic ash in the area that we can date to tell us the timing of these collisions. And it welds itself essentially to the eastern margin of the United States, creating a mountain range that would rival the Rockies that we have today. Keep in mind that this mountain range is denuded, right? There's not a whole lot of vegetation on it. There's not life on it, so it's bare rock. Bare rock weathers faster than if you have vegetation on it and trees. So these highlands are eroding pretty quickly. I'm old school, man. Thanks, CJ. You're just gonna have to help me out, man. All right. I went the other way, though. That was the problem. See? Tech. It's the beer. It's really not. So I told you that the Appalachians were actually a series of multiple collisions. We're not going to get it into today, but the next one you see coming up is Avalonia. That actually collides with us at about 350 million years, and that's where the parts of Baltic North America, or Baltic and Northern Europe, start attaching. It's actually going to swing up, and it's going to attach to the northern portion of Canada, creating the Caledonian Mountain Range, which happens in Canadian Arctic and in Scotland. So you can see both of those things. Yeah, and that's a function of that collision. And then down below is going to be the Avalonia section of Baltica, which is what's going to start attaching like New York State and Connecticut and all of those other states to us. But in the meantime, while we're waiting for this to happen, we're in the southern hemisphere. Huge hurricanes come from the east towards the west in the southern hemisphere like they do today, and they travel down the continent, right sort of in the middle of that space where there's the mountain range and the continent. See that little area of deep ocean in between there? For some reason, I don't have my star on there. We're only about, a few hundred miles away from that, and these huge hurricanes would come through, and they would take all of that sediment that was chemically eroding off of the mountain range. So granites, when they're exposed to weathering, break down into clays and take all of that sediment and just wash it down into our region downslope, into the Cincinnati region. These storms we know are bigger than anything that we know of today, and that's because we can see the remnants of them. They record their occurrence in our rocks. We need to have a field excursion so I can show you some of these things because we have ripples, like they're called mega ripples. When you go to the beach and you see the ripples in the sand and they're usually like from one crest to another, they're like this far apart. These are 6 feet apart from each other. And they're preserved in the rock. So we can see that these were incredibly large storms. Okay? And what it's doing is it's taking all that mud and it's stirring it up. I'm going to call it mud. For now, it's actually clay, which is a different thing than just mud, but mud is just the colloquial way to say it. Oh, yeah, see? No. I'm hardwired. I'm going for my beer. And so this is kind of like a diagram of the kinds of things that the waves are doing. So at the shallow parts of the ocean, they're taking all of that sediment and they're stirring it up and they're creating these gravity flows. If you've ever been, I grew up in Canada. I'm a lake kid, not an ocean kid. If you've ever stepped in a pond or a lake and you, step in a disgusting lake, which I did all the time as kids, and you, fluff up all the sediment and it stinks, and it's like, ooh. Well, think about the fact that sediment plus water is heavier than water. Right? And if you're on a ramp, gravity is going to take that over and it's going to shove it down slope in what we call tempestites. Tempestites, of course, tempestuous meaning stormy. It's a type of deposit that is generated by storms, and it basically winnows all the mud out of the seafloor and shoves it down slope and concentrates all the limestone and animal debris in the shallow areas, creating limestones. Okay, they weld together to form limestones. I'll show you some examples of these in a minute. And those welding, it's like taking a bunch of shale, sticking it in your washing machine, turning it on, all the mud gets washed out, and all you're left is with the shells of animals, right? So it's called winnowing. And that is a very, very active process in these types of tempestites. The muds that go down slope will bury anything alive in its path. This is one of the reasons why we have beautiful fossils in Cincinnati that are inflated and three-dimensional, because they're buried very rapidly. And then they're sequestered away from any kind of damage, and then they're rapidly calcified, because it's a very intense calcification process. So yeah, that's going to give us our beautiful fossils and everything, but it also gives us these layers and layers and layers of clay. And this is really important for our landslide story, if you were wondering where I was going to end up. So here's some examples of sections. Have any of you been out to the Maysville section on Route 3091 before the beautiful bridge? Okay, so this is your opportunity to go out near, take the AA highway, because the rocks along the way are like spectacular the entire time. And then the final finale is before you cross the river on Route 3071, just off the AA. There's the most extensive cut that is in Cincinnati. This is about 2 million years of geologic time, the upper cut there, so it's the most complete one out of about what we have about 7 million years here in Cincinnati. But not all in one place. So that's, and the nice thing about fossil collecting there or going to look around is that it's cut in a ramp. So you can literally park up the thing and walk across the ramps. You don't have to climb anything. It's like beautiful for fossil collecting. But if you take a really close look at some of these sections here, we can see that there is tons and tons of clay. Okay, that's from our submarine mud flows basically coming down constantly in the region through the action of winnowing as those storm waves come through and disturb the seafloor. And then as we get higher and higher up, we get these bands of limestone. Those bands of limestones represent storms coming through, sometimes one storm, sometimes multiple storms, depending on the thickness, that concentrate that debris at this location at the bottom of the seafloor. And you can see that there's a pattern to this, right, in the upper picture, that there's like a shaly bench and then a series of rocky sections and then more shale and then rocky sections and more shale and rocky sections. The way that sea level comes in and out of a region is it's a pattern. It's not random, and so we can look at how sea level changes and operates over the course of millions of years to help us understand what sea level is doing in the region, and also to help us understand the types of environments the animals are living in that are in those systems. That's a whole fun other story that we can talk about, but that's some of the ways that geologists use to tell time in the geologic record around here, because we know from modern examples and we know from the record what these cycles look like. It's all very cyclical.
The lower picture, what's the time frame between
So I'm going to say that whole unit is probably on the order of 10 to 5. We're talking hundreds of thousands of years to make the whole unit. But if you were to cross-section the shales, for instance, you would find individual beds that are instantaneous in time, like hours, that have just come through. The problem is that what geologists really have to do is not so much account for the time that's there, but account for the time that's missing. Because you're not always depositing continuously at one place. So there's gaps, and we have to learn to recognize the gaps. And so we talk about things on orders of 10 to 5, 10 to 6. This whole unit here is about is a couple million years old. So you're looking at, things on the order of 100,000 years cycles.
cycle of sea level?
That's the cycle of the sea level. It's called a parasequence. We have all these fancy words for how sea level moves and works.
Is there any changing over time?
Not that I'm aware of. I think that that's a pretty consistent thing. I mean, I'm sure that there may be changes in magnitude and maybe in terms of the speed of things as glaciers melt and so forth like that. But the natural cycles of how sea level functions over geologic time.
5,000, 10,000?
I don't know. Could be.
What was it called again?
It's called a parasequence.
So none of that is a Milankovitch cycle?
Those are all controlled by Milankovitches. Yes.
That's the further answer to your question.
Yeah.
Milankovitch cycles are based on the eccentricity of the Earth's orbit, which changes over time, the obliquity of the orbit. Those go in very predictable 40,000 year, 100,000 year cycles.
Yeah.
The weather, which then
Yeah, it's all tied. I wasn't Milankovitch. Yeah, so he. Thank you for that. He wasn't going to. That's a mouthful, but yeah. No, Milankovitch was a scientist that discovered that there is cyclicity to the way the Earth orbits and the way that, in terms of the shape of the orbit that changes around the sun on a regular pattern at 100,000 years, but also in terms of the tilt of the Earth and how that functions, that changes within a degree or so over the course and affects our seasonality, and also how the Earth wobbles on its axis also changes. And all of these affect our climate cycles, which actually help us to dip in and out of glacial episodes. By the way, we are in a glacial, if you didn't know it already. That's where we are. We're going to talk about glaciers later.
So is that the same guy who's hedging to get in and fall on the
I don't know. I don't know about that.
That was just being John Malkovich.
Yeah, being John Malkovich. Being,
Sorry.
okay, no, but you should go with that. I want to see that fulfilled. All right, so like I said before, if you were to completely denude the landscape of Cincinnati, take all the houses and everything off, for the most part, from the bottom to the top, our hills would be Ordovician bedrock. That is mainly shales and some limestones. The problem with that is that in the area of Cincinnati, we are in predominantly the Cope Formation, particularly at the bottom of our hills, which is the shaliest, clayiest formation out of our entire series. And the reason why this is an issue is because clay is an inherently weak material. It's not a strong foundation to build on. When it's exposed to weathering, it gets wet and the clay minerals absorb. They're hydrophilic. They absorb water very quickly. And much like when you get a book wet and the pages separate and you can never get it back to where it was, the clay minerals separate when they get wet. And that reduces friction between the minerals, and friction is really what we need to have everything hang on together. And so we get a lot of these little tiny mudslides that you may be familiar with, okay? So the fact that we're building on a pretty weak surface already is a hard part. Now, there's a lot of stuff that we're going to add to that. If you go into the hills and tunnel through where there's no water that gets in there, this stuff is hard mother stuff. I know, I've taken jackhammers to it. So don't get me wrong. We build pylons to help keep things into our bedrock. But if you're on a hillside slope that is exposed to this stuff, the weathering will take over and it will weaken it for you. And that's sort of the second part of our story. We are built on inherently weak material that basically becomes mud when it rains, right? But the second part of our story really is why it is that we have the slopes.